Joe. Okay, so Joe's unmuted, everyone else muted. Okay, so yeah, welcome everyone to the first part of the 25th Midwest Computability Seminar in a slightly different format. For those who might not know, our entire list of upcoming talks is up on our website, which you can get to off my webpage. And we're very happy to have Joe Miller give our first talk. He's talk about redundancy of information, lowering effective dimension. Go for it.
Okay. Yeah, so I'd like to thank the Computability Theory and Applications organizers for making this part of their schedule. And so everybody probably knows about their seminar, but check out the Midwest Computability Seminar, which meets every other week, and will sometimes overlap with CTA, but I'm not sure how much. That remains to be seen. Okay. So. Oops, I don't know what I'm doing. There. So this talk will have two parts. In the first part, and the first part's really the majority of the talk, I think. In the first part, we'll talk about a paper of Greenberg, myself, Sasha Shen, and Linda Westrick, called Dimension 1 Sequences Are Close to Randoms. That was published a couple of years back. And in the second part, the part to which the title actually refers, we'll focus on more recent work of Junlin Go, myself, Maria Soskova, and Linda Westrick on lowering effective dimension. So basically answering a question that was left open by the earlier work. You'll notice if you check out the authors of these, the paper and the collaborators for this newer work, that both have GMSW as their initials. So I'll differentiate them by using second letters when necessary. But it'll be pretty clear which parts of the talk are which, I think. Okay, so I have a slide doing a very quick introduction to effective randomness. And there's not a lot of effective randomness you need to know. You need to know roughly what Kolmogorov complexity means. Here I have the definition of prefix-free Kolmogorov complexity. Where you have a universal prefix-free machine, and you define K of sigma to be the minimum of any program tau, any string tau, the minimum of the length of tau such that U of tau is sigma. So that's the prefix-free complexity of sigma. And it's well known that you can define Martin law of randomness or characterize Martin law of randomness in terms of prefix-free complexity. Saying that the initial segments of your Martin law of random can't be compressed. Now, somewhat less well known, but actually very common in effective randomness is the notion of effective Hausdorff dimension, and that it was originally defined by Lutz. This definition I'm giving here is a characterization due to Mayor-Domo. And it's the lim inf of the complexity of initial segment over the length of it. That's the dimension of x, the complexity of the k of x up to n over n. And here, it doesn't even matter what, well, within reason, I suppose. It doesn't matter within reason what notion of Kolmogorov complexity you're using. You could use plane complexity, you could use monotone complexity. It doesn't really matter because all of those just differ by a logarithmic term. So the only place actually where it matters that we're using K is the characterization of Martin law of randomness. There's not a single time later on because we're going to be ignoring log terms throughout the rest of the talk. So there's not a single time later on where details of precise details of Kolmogorov complexity are going to matter. Okay. Now, it's easy to see from this definition that every random has dimension 1. It's also very easy to see that not every dimension 1 sequence is random, but I'll come back to that. I also want to introduce a couple of other notions, Hamming and Besicovitch distance. So the Hamming distance between two strings is just the number of differences between them, the size of the symmetric difference. So in other words, how many bits would you have to change in sigma to get to tau? And that turns 2 to the n into a metric space called n-dimensional Hamming space. We're focusing only on Hamming spaces over the 2-letter alphabet, 0, 1. That's all we're going to talk about today. Anyway, this Hamming space is one of the primary objects of studying coding theory, and we'll say more about coding theory in a bit. Now, if I want to find the distance between 2 sequences, a natural way to do it is look at the symmetric, look at the distance between, I could have written this in terms of Hamming distance, look at the size of the symmetric difference of x up to n and y up to n, divide that by n, and take the limb sup. So it's the upper density of the symmetric difference of x and y. That's the distance between x and y. It's, it's not actually a metric because it can, distinct objects can be distance 0 apart, but it's a pseudometric. And if the distance between 2 objects is 0, we say that they're coarsely equivalent. And you probably have heard, say, Dennis or Carl or Demir or many others talk about coarse degrees and that sort of thing. So this is the same notion, coarse equivalence that's used to define that stuff. Okay. So like I said, not every dimension 1 sequence is random. It's very easy to come up with an example. Start with a random y and just create a new sequence x by copying y, except when n is a power of 2, and when n is a power of 2, just put 1. X is clearly not random. Here I have a reason that only a computability theorist could love. But intuitively, you could win money by betting on X, by just waiting until you get to a position that's a power of 2, and then you know it's a 1. Okay, that's an impractical way to win money. You might as well just go to work, because it's going to take you exponentially long to, never mind. Anyway, it's a bad way to win money. But on the other hand, we've only slightly lowered the initial segment complexity of X, so its dimension is still 1. To get from X back to Y, you just have to give me logarithmically much information, and that disappears in the limit used to define dimension, right? But what we showed is that every dimension 1 sequence is close to random. So a sequence has dimension 1 if and only if it's coarsely equivalent to a random sequence. Another way of thinking about that is that the silly example I gave above is kind of the only way you can build a dimension 1 sequence. Start with some random and change its positions on a sparse set, in this case, meaning a density 0 set. The proof uses a theorem of Harper about Hamming space. I'm not going to tell you, well, okay. I'll tell you what Harper's theorem is. Not how we use it, but what Harper's theorem, all it says is that if you look at a Hamming ball, I'll define that in a moment, but it's what you think it is, around the all 0 sequence and a Hamming ball around the all 1 sequence, with whatever radii you want, those are as far apart as any 2 sets of that size can be in Hamming space. That's not that shocking. Apparently it's hard to prove though. Anyway, and using Harper's theorem, you can prove the finite version of this, a version of this theorem for finite strings. And then you can't just quite use the greedy algorithm to sort of blockwise use the finite version to get the infinite version, because the greedy construction would possibly run you into a dead end. But you could look at all possible constructions you could use, that they form a tree, show that tree never dies, so it has a path. So there's a compactness argument. There's a little bit of subtlety there, but not much. It follows from a little bit of compactness and the finite version. Okay. Well, not really the finite version, but the math that you would use, never mind. It's the same combinatorics on the finite side, and then you need some compactness. Okay, so we know how to effectively raise the complexity of a dimension 1 sequence to get a random. What's next? Well, we could ask how hard it is to increase the complexity of a dimension T sequence to get a random. In other words, what's the Besicovitch distance from a dimension T sequence to the nearest random sequence? Equivalently, a dimension 1 sequence, because once you've gotten to a dimension 1 sequence, going to a random doesn't take any distance, right? Doesn't add any distance. So what is the distance from a dimension T sequence to the nearest dimension S sequence? So how do you don't want to raise the the complexity by all the way to 1, but you want to raise the complexity a little bit. How hard is that? In other words, in terms of Besicovitch distance. What about lowering dimension? The distance from a dimension 1 to the nearest dimension t. And finally, from dimension s to dimension t, lowering dimension in more generality. And that last question is part 2. These first 3 questions were answered in the 2018 paper, and I'll talk about those answers. The last one is what was left open in that paper, and I'll talk about why there's an extra obstacle there. Okay, but we need to learn a little bit more about coding theory, a little bit about coding theory. We really haven't done any yet. So the Shannon entropy function is this function here, h of p, negative p times log of p minus 1 minus p times log of 1 minus p. And I have it graphed over here. See this nice graph. Beautiful curve. The way you should think about it is that h of p is the information content of one coin flip with probabilities p and 1 minus p. So you have an unfair coin, you flip it once, how much information does that give you? Well, okay, that's the kind of intuitive way of thinking about it. But let me say a few words about that intuition. If you have a fair coin, in other words, the probabilities are 1/2 and 1/2, you're up here at 1. In other words, 1 bit of information. That coin flip gave you 1 bit of information. If it's completely unfair, it always lands tails or always lands heads. You have 0 information in either case. And then this curve inexplicably smooths that out and tells you how much information you get for every other case in between. I'll explain this intuition, but that's the intuition I want you to have. I've already talked about Hamming balls a little bit, but obviously the Hamming ball of radius r centered at sigma is exactly what you would expect. We give it the notation br sigma, and it's just all taus that are within r of sigma. Now, we're going to use VNR for the size of Hamming ball of radius r. And it's not hard to see that all Hamming balls of radius r in 2 to the n have the same size. Think of, one way to see this is think of 2 to the n as the n-dimensional vector space over the finite field with 2 elements. And then you can just translate any Hamming ball of radius r onto any other one, so they obviously have the same size. I don't know if that's clarifying or not. It helps me, but everyone has their own way of thinking about things. I think you'd be more surprised if I told you that not all Hamming balls of radius r have the same size. Okay, so what's the connection between the 2 things I just introduced? Well, if r is less than n over 2, so if the radius isn't too big, then, and here's the important part, the log here of VNR is approximately equal to h of r over n times n. And so it's less than or equal to that, and it's greater than or equal to that up to a little o of n term. Actually, it's going to be logarithmic even. Oh, is it? Yeah, I think, it's logarithmic. Okay, so let's just copy that over and in a little bit less detail, just to say that log of VNR is approximately equal to h of r over n times n. Now, why do we care about this? This is the very standard approximation for the size of Hamming balls in terms of the entropy of function. It's why every formula I write down from now on is going to have the entropy function somewhere in there. Well, it's easy to see why it's interesting to us in the following proposition. If sigma in 2 to the n has pn1s, then its complexity is at most h of p times n plus some little o of n term. So it's essentially sigma can be compressed to a size of at least h of p times n. Why is that? Well, first of all, if it has pn1s, then it's in the ball of radius pn around the all zero sequence. And there are vn, pn strings in that ball. So we can give each a description of length log of, and I didn't say it before, but hopefully it's clear. Every time I say log, I'm talking about log base 2. So we can give each a description, a binary description of length, approximately log of vn, pn. which by the lemma above is approximately h of p times n. And that's all I'm saying in the proposition. That proves the proposition. Except the lemma only works for radiuses less than n over 2. So that last approximation is only true for p less than or equal to 1/2. But if p is greater than 1/2, switch the roles of the zeros and ones and use the fact that the entropy function is symmetric, h of 1 minus p is equal to h of p, and you get the same bound. So I put that in gray because I don't want you to worry about it that much. The bound works in either case, but I spent too much time talking about it already. Okay, so we get that if x has asymptotic density p, and its dimension is less than or equal to h of p, so we're already kind of getting a nice connection between, density and entropy. One important case of sequences that have density p are the Bernoulli p randoms. So you can think of these as being generated by flipping that unfair coin I was talking about before, where heads is probability p and tails is probability 1 minus p. Each coin flip is independent. You can effectivize this definition and talk about this the same way we talk about Martin law of randomness, but I just want to give you the intuition for what a Bernoulli p random is. And these, unsurprisingly, have density p. One has probability of p of coming up. That's what you would expect. It's the law of large numbers. And it's not too hard to show, and we already have one direction of it, that if x is Bernoulli p random, then its dimension is h of p. We have the upper bound of the dimension already, and the lower bound is basically that there are enough strings of density roughly p that a randomly chosen one can't be compressed too much. So you go through that, and it's not too surprising. Okay, so just copying, well, nope, not just copying what I had. Okay, so that's Bernoulli p randoms, and we'll come back to them in a moment. First of all, let's talk about the best case. What I want to do is establish how close can a dimension S ever be to a dimension T sequence. And whenever I talk about closeness or distance, I'm talking about Besicovitch distance if I'm talking about infinite sequences. So we're going to restate this proposition, but this proposition gives us what we want. If the distance between x and y is p, then we can bound the dimension of y in terms of the dimension of x plus the entropy of p. So why is that? Well, say that we have a y up to n and x up to n that differ on density roughly p. To code y up to n, all I have to do is tell you x up to n and tell you where the pn changes are. But to tell you where the pn changes are, that's giving you a string of length n with pn ones. So in other words, I can code y up to n given a code for x up to n plus hp of n more bits of information. And you get this inequality. And from now on, just to be clear, from now on, I'm going to stop writing little o of n. And anytime I'm doing something approximately, I'm going to use notation like that. And just suppress as much of the kind of log terms and other little, annoyances that would otherwise complicate matters. Okay. Now, rearranging that, first of all, if you look at the proposition, you solve for h of p, you see that h of p is greater than dim y minus dim x. By symmetry, it's also greater than dim x minus dim y. So it's greater than the absolute value of the difference. And therefore P, well, here we need to use that H inverse is, H inverse is an increasing function because it's just going, it's just going through from the inverse function. I didn't say this before, but when I talk about H inverse, I'm only talking about the inverse of the entropy function restricted to 0 to 1/2. Otherwise, it doesn't, we need to restrict it so that it can have an inverse. So H inverse mapping 0 to 1 to 0 to 1/2 is an increasing function. So we can apply H inverse to both sides and we get this, I'm pointing to the wrong screen. I'm pointing to this screen here. I can point to this screen. we get the distance between x and y, if x is dimension t and y is dimension s, is greater than or equal to h inverse of the absolute value of s minus t. And that's just taking the proposition and flipping perspective so that you start with the dimensions of the two sequences and then you try to figure out what the what you can say about the distance. Okay. Moreover, it really is the best case. This is the amount of distance necessary between a dimension s and a dimension t, and it's achievable as long as we get to pick both sequences. We proved that it's a construction. You really have to do a little bit of work, but you can find a dimension t sequence x and a dimension s sequence y, whose distance is as small as it possibly can be. So this is the absolute best case, as close as dimension s and t sequences can be to each other. Can you always do that well if you fix the lower dimension sequence? If you fix a dimension t sequence x, can you always find a y that close? And the answer is no. And the counterexample is simple, and it's going to be our first use of Bernoulli randoms, maybe our best use of Bernoulli randoms, to be honest. If x is a Bernoulli h inverse of t random, why did I choose h inverse of t? Well, that's so the dimension is exactly t. And it also means that the density of ones is h inverse of t. Well, now we take a dimension s sequence y, and knowing that it has dimension s, we know that the density of ones in y is at least h inverse of s. If it drops below that infinitely often, then we can compress it too much, and the dimension is too small. So therefore, to get from x to y, you have to add at least h inverse of s minus h inverse of t ones. So that's the lower bound of the distance. Now, it's not entirely clear, even if you've been working with this function for a while, that h inverse of s minus h inverse of t actually is greater than h inverse of s minus t, but it is. Most of the time it's greater. Sometimes it's equal. Here I have the picture. I haven't labeled it, but the top function is h inverse of s minus h inverse of t. That's the top function here. The bottom function is the other one, h inverse of s minus t. And you'll notice that the only times that they can even be equal are when t is 0 or when t is s. This is graphed for s equal to 1/2, but it's the same for any other value. So t is 0, t is s, those are the only times that you get equality. Okay, so you can't go from a Bernoulli h inverse of t random, which has dimension t, you can't go from that to dimension s in the optimal possible, the best possible distance. On the other hand, that simple obstacle actually is the worst case. If t is less than s and x is dimension t, then there's always a y with dimension s within h inverse of s and h inverse of t. So that's really the worst case, and so easily witnessed, which is nice. And there are some similarities to the proof that dimension 1 sequences are close to randoms, a proof I didn't tell you much about, to be fair. The analog for finite strings, again, follows from Harper's theorem, and isn't too hard given Harper's theorem. It's pretty easy given Harper's theorem. And the construction is done blockwise, and then we use compactness because of this kind of problem that you could run into trouble. The reason you could run into trouble is that when you're adding information early on to x to get up to y, that information could correlate with information later on in x. So you might be adding information here and dropping the complexity of x later, the relative complexity of x later. So that's the dead end you can run into. But that's a weird thing to happen. If you're just adding information fairly randomly, you wouldn't expect it to happen, which is why some construction will work. But there's a new difficulty, and it's a serious difficulty. X can have regions of complexity higher than t and regions of complexity lower than t. So what if we are looking at a block of x that already has dimension s? Do we just say, we're winning, let's not make any changes, and save those possible changes up for maybe later blocks that have really low complexity? Or do you say, look, I've been assigned this many changes to this block, a density of h inverse of s minus h inverse of t, and I'm going to make them no matter what and push the complexity up as high as I can. These are two strategies we argued about for a while to try to figure out which was the better one. Notice in the first strategy, basically the first strategy is where you make sure in your construction that you're getting up to a dimension s sequence, but you're a little bit loose about how many changes you're going to make. If the complexity is too low, you make more changes than are allowed. If the complexity is too high, you make fewer changes than are allowed, and you hope that it all works out in the end. On the other hand, the second construction, where you always use the right number of changes for that block, well, then you know the distance is right, but you don't know that you actually got up to the dimension s. So there's a verification that has to be made in either case, and it wasn't clear which one was easier. And what ended up happening was that we needed both constructions because we could get the verification, I'm not sure what I said before, the verification to work out for one construction for some pairs S and T, and for the other construction for some other pairs of S and T. In fact, they were perfectly complementary, except that shared a boundary. So there are actually two constructions, conditioned on which of these terms is larger, 1 minus t times h, the derivative of h inverse of t, and the same thing for S. And as far as we can tell, both constructions are necessary. So that was kind of a fun difficulty. And the constructions are both proved to work under the respective assumption using a somewhat delicate convexity argument. So this was the hardest result in the 2018 paper. But let me move on. Oh, not quite move on. Here, I'm showing you the functions, h inverse of s minus t and h inverse of s minus h inverse of t, where s is equal to 0.99, which might seem like an odd choice, but I'll say more about that. And you can see, you can see that there really is a difference between the best and worst cases, a pretty big difference in this case for such a, for such a value of s. And if you look at it for a little while, you realize that it's rotationally symmetric. And it's not hard to see it's rotationally symmetric. You don't have to dig into the inverse entropy function to figure this out. It's just a simple algebraic, it's just a little simple algebra to show that this is actually rotationally symmetric, which is weird because I have no idea why that would be. There's no a priori reason or no post hoc a priori reason I can find for why this should be rotationally symmetric. And I'd be interested, if somebody has an intuitive argument for why that should be expected, or maybe that's just a coincidence, the kind of thing that happens when you do this kind of math. And it would be rotationally symmetric for any value of s. The reason I chose s to be so large is that it's easier for values really close to 1 to see that it's not symmetric under reflection. There's more over here than over here. There's more over here than over here. It's not reflecting across the red line doesn't give you symmetry at all. And that's also true for any value of s, but for values that are further away from 1, these regions get really thin and it's really hard to tell. Anyway, so that's what it looks like. Okay, now that answered the whole question about increasing dimension and how many bits you'd have to change to increase dimension. How about decreasing dimension? Well, here we have to talk a little bit about coding theory again. And Delsart and Perret, I have no idea if that's how you pronounce their names. I'm assuming they're French. They showed that you could cover the Hamming ball of dimension n, the Hamming space of dimension n, with 2 to the n over VNR Hamming balls of radius r. This is called a covering code of radius r, the collection of centers. And notice that this is, notice this expression is actually a lower bound on any possible cover because the Hamming balls only cover VNR points and there's 2 to the n points in the space. So you need at least this many Hamming balls. And what Delsart and Perret say is that you can get by with just about that many. I should be honest, there's a hidden term here that's linear in n. But we're going to take the logarithm of this and divide by n. And so that's one of those order log n terms we don't really care about. Okay. So what they say is you can essentially optimally do that. The lemma is proved using a probabilistic method. In other words, you prove that if you choose the centers randomly, enough centers randomly, then with positive probability, it has the properties you want, has the property you want in this case. And so it's not a constructive proof, but this doesn't bother us. You can find such a code via an exhaustive search. We're not worried about efficiency right now, just we want things to be effective though. Okay, and now let's pick R to be Pn. And so we know that there's, by the lemma, that there's a covering code of radius Pn and size roughly equal to 2 to the n over V n Pn. And for every center in that code, you can give a description to that center because you can effectively find such a code. You can give a description of that center in log of the size of the code, many bits. And now that's n, again, I'm pointing to the screen, n minus log of vnpn. But now we use our approximation of v of the size of a Hamming ball, and we get 1 minus h to p times n. So what are we saying? We're saying that every sigma is within, okay, now I flipped things around a little bit here, but it really does follow from what I just said. Every sigma is within h inverse of 1 minus t times n bits of a string tau that has complexity roughly t times n. Well, less than or equal to t times n. Could be much lower, but no, not much higher than t times n. Okay, first of all, we have a covering code. So you take any sigma, it's close to one of the centers. How close? Within the radius. What radius am I taking right now? I'm taking the radius h inverse of 1 minus t times n. Plug that into here. So we're letting this be p. So we plug it in here. And h of h inverse of 1 minus t is just 1 minus t. And so we get 1 minus quantity 1 minus t or t. Great. Hopefully that little bit of manipulation wasn't too hard. Okay, so I've rewritten that. Every sigma is within h inverse of 1 minus t times n bits of a string tau that has complexity no greater than essentially t times n. And if you just, and there's nothing to this. This is the easiest proof in the 2018 paper. If you simply apply the proposition blockwise to y, to an infinite sequence y, lowering the complexity of each block blockwise, then you can show that for any y and any t, there's an x of dimension t, which is within distance h inverse of 1 minus t. Just apply it blockwise. Well, you have to be a little bit careful. The blocks should grow. Why should they grow? Because everything I've said up till now has been approximate. I mean, we have these like squiggles everywhere. And when the blocks grow, those approximations get better and better in the limit. At least when you divide by n, they get better and better in the limit. Those log terms go away. So the blocks have to grow. But if they grow too quickly, then you can't reason about what's happening in the middle of a block if you look at an initial segment that cuts in the middle of a block. So all you have to do is let the nth block have size n, and it works. But it is the easiest proof because you really are just taking the finite result and applying it blockwise. No compactness trickery or anything like that. Applying this to a sequence of dimension 1, if you start with a sequence of dimension 1, where you know you can't get down to dimension t any better than h inverse of 1 minus t, well, this tells us that there's something of dimension t exactly that distance away. So in other words, starting from a dimension 1, the best case bound is always achieved when we're trying to lower dimension, which is all you, I mean, obviously if you're starting from dimension 1, you want a lower dimension, you can't raise it. Okay, so hopefully that makes sense. I'll show you another picture. It looks a lot like the last picture. So here we have the worst case from a dimension t to the nearest dimension s, where s is 1/2 for this picture. And here we have the distance from Nope, sorry. I didn't say that right. Here we have the worst case from a dimension t to the nearest random. So S is 1, actually. And here we have the distance from a random to the nearest dimension t. Also, this is the best case of a dimension from the distance of the distance from a dimension t to the nearest random. So this really is the best case curve and the worst case curve for going from t to a random. But the best case is also always achieved for going from a random to a dimension t. So every random is close to a dimension t sequence, but not every dimension t sequence is close to a random. This bothered me initially because I don't know why. I mean, it's not that hard to imagine such a situation. But once I had the right analogy that every taco truck is near a corner, but not every corner is near a taco truck, I was like, yes, okay, now I get, that's a little bit of political, by the way, but now I get why, what's happening here. And basically you have different kinds of dimension t sequences. You have ones that are near randoms and you have ones that are far away from randoms. Okay. So we've really answered the first 3 questions on that slide that had 4 questions from about a half an hour ago. We've raised dimension from anything to anything, and we've lowered dimension from 1 to anything. So what about going from a dimension S to the nearest dimension t less than or equal to S? Can you always do that optimally? You can do it if S is 1. What about for a general S? No, of course not, because I still have some more talk. If information is stored redundantly, it's harder to erase. You can store information redundantly in a dimension 1, not in a compact way, not in a useful way. So let's look at the simplest possible example of storing information redundantly. Take a random z and look at y, which is just c joined z. So you're just repeating every bit twice. Of course, the dimension of y is 1/2. And for a contradiction, let's say that you could lower the dimension of y to 0, only making h inverse of 1/2 changes, density h inverse of 1/2 changes. So this is the best case. Can you do it? No, we've made it harder to erase information. We've copied the information twice, but I want to just go through and prove it. Okay, so we can code y up to 2n by giving 1, a description of x up to 2n, 2, every time you see x of 2i not equal to x of 2i plus 1, you know one of those bits got changed. So you have to, so give me the value of y of 2i. Tell me the correct value. 3. Sometimes both bits were changed. So there are going to be some times when x of 2i is equal to x of 2i plus 1, but not equal to the original value y of 2i. So give me a description of that set. Okay. So how hard is it to give a description of x up to 2n? That's just k of x up to 2n. Now, like I said, I can actually recognize the pairs that are not equal, that should be equal. So how many pairs could there possibly be? Well, I'm making only h inverse of 1/2 times 2n changes, right? So there are most that many pairs. If every change was just messing up one of the pairs, and I only have to give you that many bits of information to correct the pairs, because you can find the pairs. That's the easy part. Now it's a little bit harder for these pairs where I changed both bits. Now I really have to think of this as a subset of n of size h inverse of 1/2 times n, right? But now, so in other words, I have a sequence of length n, and I want to mark the positions where you made the changes. And why is it h inverse? Why is it a 2n here and an n here? Because here I'm only changing 1 bit, here I'm changing 2, so I can do half as many. Okay, so so it has the description of length h of h inverse of 1/2 times n. This is going way back to our original. If we know the density of ones in a sequence, we can compress the sequence. We know how to compress the sequence. So it's h of h inverse of 1/2 times n, or n over 2. Putting it all together, we know that k of y up to n can be given a description essentially of the form, a description of x for the pairs that that differ, correct them. And for the pairs that don't differ, because both were changed, you have to tell me which pairs those are. And that's roughly equal to n, because x has dimension 1/2, in fact, in a very regular way. So solving for k of x up to 2n, that's greater than or equal to n over 2 minus h inverse of 1/2 times 2n. And you plug that into a calculator that can handle the inverse entropy function, and you get that that's roughly 0.2 times n, which is not conducive to making x a dimension 0 sequence. And we didn't even try that hard. We basically were assuming that in the worst case, all of our changes were both being used here and here. We weren't even being clever. I just want to make that clear. Okay, so x can't have dimension 0. That's a contradiction. Notice the contradiction was only rhetorical. I never actually used the assumption that x was dimension 0 in the proof. It really wasn't a contradiction. But rhetorically, I think it made more sense. So what can you do? How easily can you reduce decrease dimension? You can't always do h inverse of s minus t. In fact, it's a lot worse than that. If y has dimension s and t is less than s, then there's an x with dimension t within the distance. Well, if t is small enough, the distance is h inverse of 1 minus t. Think about that for a moment. That's no better than if you started with a random sequence. On the other hand, if t is big enough, it's close enough to s, then you get this expression. Well, I'll show you some graphs, so don't worry too much about that expression. Okay, furthermore, these are tight. For any s, you can find a sequence y sub s of dimension s such that you can't do better for any t. So you only need one sequence for each y, and that works for all t's. So, okay. So again, I've already said this, but if t less than or equal to s is small enough, we can't lower the dimension at all any better than if it were random. We can't leverage the fact that it has dimension s. The redundancy of information, the robustness of the coding is such that we might as well, even though it doesn't have full information, it might as well. In particular, and this is what's kind of striking for me, the distance from ys to the nearest dimension 0 is 1/2. And you can always get to a dimension 0 by changing half of the bits. And here, ys is so redundantly coded that you have to change half the bits to get to a dimension 0. Okay, that was a little surprising to me. Another observation, we can always, if we're only allowed to make a few changes, a small density of changes, we can always lower the dimension. And this is because, well, it's true that for all s greater than 0 and all epsilon greater than 0, there's a t less than s where the worst case is less than or equal to epsilon. So if we're allowed to make a density of epsilon changes, we can lower to t. And how can you see that? Well, look at this term here. As t approaches s, t only appears in the numerator. As t approaches s, the numerator approaches 0. So we know that this is actually approaching 0 as t approaches s from below, and that's what this observation is saying. It needs to be checked, but the function is continuous and even differentiable, as long as you stay away from s equals 0 where weird things happen, but don't worry about that. Is there a simple reason that this has to be the case, or is this another just like nice coincidence? I think there must be a good a priori explanation for this. And the second case, and this is a little bit stranger, this might just be a coincidence, but the second case, notice, is linear in t. All these functions are these nice curves, and here you have a linear function. And everything I've just said is clear in the following graph. Here we have fixed dimension s to be 1/2, and we're looking at going from 1/2 down to t less than 1/2. The bottom is the best case. It's the same thing we always have, h inverse of 1/2 minus t. And the top is the weird function I just showed you. Here's the case transition. And the dotted line here, which actually overlaps up here with the solid line, is the distance from a random to the nearest dimension t. And notice that they agree for a while, then there's a case transition, and then the second case is linear, it just directly goes from there to 0. So that actually simplifies. I mean, if you think about what this is saying, once you know what this case transition is, and you know that this is a linear function that has to end up at 0, like whatever I wrote down, who cares? Now you know what function that is, right? Anyway, let's flip our perspective, fix t, the lower dimension, to be 1/2, and look at compressing down from, or not compressing really, but dropping the dimension of a sequence of dimension s down to dimension 1/2. As you see, for large enough s, you can't do any better than random. And then once you hit the case transition, you can do better and better and better, of course. And the bottom is the same function we always graph, h inverse of s minus t, h inverse of s minus 1/2 in this case, the best case. Okay, so that's what that looks like. Now, where does that come from? All right, so what we have to think about is really the finite case. How do we code information robustly? Now, I said redundantly before, and I think redundantly is a good word. I put it in the title because it points your brain in the right direction, but it doesn't get you all the way there. Because you know what it means, and we've already done it, to redundantly code 3 bits in a 6. But how do you robustly code 4 bits in a 6? Easy. You copy each bit 1.5 times. Obviously, but what does that mean? So I'm going to use the word robustly now and give you a precise definition of what I mean. Not really a definition, example really. I'm going to show you what I mean. And for that, we're going to go back to covering codes. So this is just I've copied Del Start and Perret's result, that there's a covering code of near optimal size and radius r. So now let's fix any tau and any q greater than r and ask how many centers from C, how many elements of C are in the Hamming ball BQ tau? How many should we expect there to be there? Well, we can just do a little probabilistic argument. Each sigma is in V and Q balls of radius Q. Okay, why is that? Well, if sigma is in the Q radius ball around tau, then tau is in the Q radius ball around sigma. So that's just counting all the centers tau, all the centers tau, all the possible taus whose balls capture sigma. So if you randomly choose a Hamming ball of radius Q, the probability that sigma's in it is VNQ over 2 to the n. That's just a simpler way to see that is actually just a volume argument. So on average, we should expect BQ tau to contain, well, there's size of C centers and the probability that each one is in the ball. And when you simplify that, you get approximately VNQ over VNR centers. And that's what we want. We want our covering code not to be clumped. We don't want the elements of our covering code to be clumped so that we don't want any ball anywhere to contain too many of the elements. We want it to be evenly distributed. So such codes exist. There is a covering code of radius r of approximately the right size, such that for every q and every tau, the size of BQ tau intersect C is no larger than what we would expect it to be, VNQ over VNR. Again, there's a linear term there, a little worse than in the Del Start-Perret result. And there's a linear term there. But, again, these are going to go away when we take logarithms and divide by n. Again, it can be proved using the probabilistic method. It's not too hard. I'm not claiming, we prove this in our upcoming work, but I'm not, just because I haven't found anyone else having proved it yet, I'm assuming somebody else has proved this at some point. I just haven't seen it. And so it's very standard techniques. Okay, so now what I want to claim, and I'm going to build up to that claim, but what I want to claim is that if you randomly choose an element of C, then that string is a robust string of the appropriate complexity. Okay, so fix n and s, and let C be as an lemma for, well, h inverse of 1 minus s times n, the radius h inverse of 1 minus s times n. That radius is specifically chosen, and let's not go through the calculation this time. It's the same kind of thing we've been doing all along. Specifically chosen, so the size of C is 2 to the s times n. So if we randomly pick an element of it, well, every member of that cover can be compressed to size, can be given a description of size roughly s times n. And if we randomly pick a member, it's going to have complexity as high as possible, so essentially s times n. So we have this string sigma of complexity s times n, such that if we change it on density h inverse of 1 minus t to get another string tau, then k of tau is at least approximately t times n. Now notice, this is the same as if we started from a random, right? So this is the worst case. Okay, so this is the claim. If we change that sigma on density h inverse of 1 minus t to get a string tau, then the complexity of tau is pretty large, greater than or equal to t minus n. Okay, now why is this? Because if you give me q equal to h inverse of 1 minus t, sorry, let's try it again. Let q be equal to h inverse of 1 minus t. We can determine sigma, give a description of tau, and an index of sigma. So we know that sigma is in the ball of radius q around tau, and we know that it's the center, so we know it was chosen from C. And we also know that there aren't that many centers in BQ tau. In fact, you do the calculation, it's VNQ over VNR, that's approximately equal to the quantity S minus T times N. So all I have to do is give you a description of sigma, is give you a description of tau and an index of sigma in this set. But that set's not too big. So what does that mean? It means that k of sigma is less than or equal to k of tau plus s minus t times n. We also know that it's roughly complexity s times n. Solving for k of tau, we see that k of tau can't be too small. It has to be at least approximately t times n. So there is a sigma such that k of sigma is approximately s times n, and we cannot lower it to something of dimension less than, of complexity less than Tn any easier than if it were random. The distance between sigma and tau, I flipped this around, sorry. Let me, I'm gonna copy that proposition up here and then, right. So the point is that if the distance between sigma and tau is less than or equal to h inverse of 1 minus t times n, then the complexity of tau is at least t times n. But like I said, you can't do better than that. That's as bad as a random. So you have something of complexity s times n, such that it's just as hard to lower its complexity to Tn as if it were a random. So this is the robustly coded string. It's only coding s times n bits of information, but it's coding them in such a way that you cannot lower it at all any easier than if it were random. Okay, that was a lot, but the thing, and this is why I put this in a blue box. I wouldn't use shaded boxes at all in the talk. And I know we're all tired. I'm tired. But I want you to know that I can always robustly code information in finite strings such that it is maximally hard to drop the complexity of that string. The other thing I want you to notice is that I've already told you that things are different for infinite sequences, at least when t less than s is not too small. When t less than s is small, it might be as hard as if you're starting from a random, but when it's close to s, it's not necessarily that hard. We have that linear part of the function. So we have a situation, all of the other, things that I told you about, the the result for infinite sequences was an analog of the result for finite sequences. Here we have a situation where the result for infinite sequences is not. It is for some pairs of values S and T. It's not for all the pairs of values S and T. Now, I was going to say a few words about the proof of this, but I think that I've said enough. So I'm going to leave it on this result and just leave it a complete mystery. I mean, unless you want to talk to me afterwards a little bit. So thank you.
Great. Yeah, thanks, Joe. Yeah. If we can hear the applause.
Who's doing that?
What? I am.
Was that as you? Okay. Well, thank you.
So are there any questions for Joe? You can just jump in. What is the bird? Questions? Okay. Well, if not,
if no questions, why don't we let Joe finish the proof?
No, I wasn't going to give a proof, but I could say.
Yeah, go for it.
Okay. Well, very quick sketch. The strategy that lets you actually do the reduction better than the worst case alternates between leaving intervals unchanged and saving up some changes that you can use later, and then making lots of changes later. So you have this savings block and a spending block. And the density of changes that you need to make and the relative lengths of the savings and spending blocks, you can just set up some, you can set up the equations that tell you like how much you could drop the complexity making this many changes and with this ratio. And then it's just an optimization problem. To get the formula, it's just calculus. To show that it's optimal, you have to do a little bit more work, but to get the formula, it's just calculus. And I can even tell you what's the difference between the infinite and the finite case. In the infinite case, the way we leverage the fact that we're starting from a dimension S is that we don't switch from savings to spending until we get to an initial segment of complexity S times this length. So that's how we use the fact that Y has dimension S. If you look at a finite string, it may be that every initial segment looks like, has complexity that's too high, and you only get to complexity S times the length at the end of the string, essentially. And that's exactly what's going to happen for these robust strings. So there's a difference between the finite case and the infinite case, is that the infinite case has to drop down and witness dimension S infinitely often, and the finite case only has to do it at the end, and you can't leverage it. So that's all I want to say.
Any other questions or comments?
Well, there were none to begin with, so other ones are probably unlikely.
Or encouragements to do more.
You had several results saying given X, there is a Y with a certain property at a certain distance. How about the complexity of Y in comparison to X?
So I think it's, we didn't really dig into it too deeply. I think you can probably do it at worst case, it's like 2 jumps. For the worst arguments, and 1 jump and actually might be computable for some of the arguments. So some of the arguments are probably computable. Some of the arguments you actually need to know, complexities of things. And then there's this compactness part, so that might add not a full jump, but like a PA degree above whatever oracle you're using to construct the tree. So some of them might be worse than a jump. I'm not sure. Lowering dimension, I think, is just a jump. Increasing dimension might be a little bit worse.
Thank you.
And I guess it's related, just occurred to me, probably makes no sense, but you're talking about the taco truck phenomenon and things not being close. That is there any chance there's any connection between that kind of thing and broken dimension phenomenon?
Okay, so that's a really good question, and And the short answer seems to be no, and the long answer seems to be no. We looked into it a little bit. Linda Westrick visited, and we tried to understand, we have all these different ways to distinguish dimension 1/2 sequences, including how much information you can extract from them. And we tried to find relationships between them. And what we found was non-relationships. So, so there might be something there for extreme values. I'm not sure, but in general, I think there's nothing there. Nothing very very general is there.
Got it.
Yeah.
Other questions?
Yes, if I may. Are there connections with the results of coding theory?
Well,
correcting codes.
Okay, so two things about that. One is, coding theory is mostly involved in trying to find efficient codes. And so the results we're using from coding theory, these existence results, that they mention in passing usually, but they're not super interested in, because what they would like to do is be able to compute these codes very efficiently. They just give kind of, theoretical bounds. So that's one thing to say. The other thing is that actually covering codes are sort of dual to error correcting codes. Error correcting codes are, well, in the simplest case, generally if you're thinking about error correcting codes, you're thinking about a packing code. How many balls of a certain radius can you pack into Hamming space? Which does turn out to be quite different than how many balls of a certain radius you need to cover Hamming space. So most of coding theory actually looks at the packing problem, and the covering problem definitely is secondary. Our robustness, though, is interesting because the robustness of this covering code says that you don't need much information to correct. No matter how badly you change things, you can correct with the minimum amount of information. But you might still need some, even for very small changes. And that's not good for error correcting. Error correcting, you want packing because you want to know if you've made only a few changes without any help from anybody, you can get back to the code word. So two differences: we don't care about efficiency, and we're looking at covering codes instead of packing codes. Although there is a whole book on covering codes called Covering Codes. So it is interesting to coding theorists, but it's not as interesting as packing codes.
Thanks.
Thanks. Any other questions? Well, if not, thanks again, Joe. And so I think in CTA tradition, we will hang around, and people who want to